time, what we have discussed the merits and demerits of steel construction, and we have also overviewed various design specification and design methods, where we have discussed in detail the allowable stress design and also the LRFD design along with plastic design.
सर वो शायद नहीं था किया हमने LRFD और प्लास्टिक.
Okay. LRFD and ASD design was not covered, you are saying?
नहीं सर, ASD कवर किया था, वो दूसरा LRFD और प्लास्टिक वाला नहीं था किया.
Okay. I will start from that. Okay, Bismillahirrahmanirrahim. Okay, last time I have explained the allowable stress design in detail. So actually, what is the difference between ASD and LRFD? So I told you that our basic design equation is this one, the same, which is added top. So what we do, we apply the external load effect with factor of safety, and then we equate with the resistance offered by a structural shape of a material. So actually, when we multiply the applied load effect with factor of safety, so we are bringing the structure from state of collapse to the safe state. So we have already discussed that why we use factor of safety. Actually, in ASD, what we used to do, we bring the factor of safety on the right hand side, and we divide the resistance of a material with the factor of safety. And factor of safety value is 1.67 in both design methods. Either this is ASD or this is LRFD. But actually, in this LRFD, what we do, so if I am writing this equation in arithmetic form, so we represent the external load effect with a general nomenclature or general constant Ra, and resistance of material is, or resistance of the structure is represented by Rn. So if external load effect is multiplied with F, then this left hand side should be equal to the resistance of structural components. So further I told you that this applied load effect, actually applied load effect may be the tension, maybe compressive force, or maybe the any other type of the shear force or bending moment. Even though they are shear force and bending moment on the beam, so shear force bending moment, they are also the function of the load acting on the beam. So on the load, total load may be the summation of dead plus live load. So here I am just in generalized form, I am representing the applied load effect or in terms of summation of dead load and live load. There might be many other loads. There might be earthquake load, there might be wind load, but for the simplification, I am just considering the dead plus live load. So then we are having the factor of safety, and this is the resistance of structural component. So what we do in LRFD, we divide the, or we convert the factor of safety into two parts. Maybe, for example, one part will be F1 and other part will be F2. We convert into two parts, and F1 multiply F2 will be equal to F1. The simple example will be that if F is 12, so F1 may be 4 and F2 will be 3. So 4 multiplied by 3 will be 12, so answer will be same. So what we do, we distribute the factor of safety into two parts. One is the major factor of safety and other is the minor factor of safety. Major mean that which is having the larger magnitude, and F2 which is having the lesser magnitude. So what we do, one part which is the major part, it will be multiplied with the load effect Ra, and load effect may be the summation of dead and live load and all other type of the load. And the smaller factor of safety we bring on the right hand side. So resistance of the structural member is divided with the F2. So please note that F1, F2, both values are more than 2. More than 1. So factor of safety is always more than 1. So here 1 and 2 just I'm using for reference for your understanding. So further, if 1 over F2, we are considering that 1 over F2 is represented by a value 5. So 5 value will always be less than 1 and which will be referred as a strength reduction factor. And on the other hand, actually F1 is not the same value. So I am representing F1I. I is the index, it meant this is a variable. So this F1 will be a if it is multiplied with the dead load and live load, so this will be a different value. So F1 will be the factor of safety for dead load. It's रोल नंबर
सही।
मैंने आगे इनको उनके मुझे सेंड कर दो
ओके
और
सर।
उनको ऐड
और
किया
सर सर हमारी जो वो स्टील की लैब है ना उस पे उसके लिए ना एलएमएस पर कैपेसिटी सिर्फ 1 है, तो वो बच्चों का रजिस्टर नहीं हो रहा, तो वो भी कह रहे थे कि सर से
मैं भी
बात
कर
करें।
देता हूँ, मैं भी कर देता हूँ, आपने मुझे
ओके
टेक्स्ट मैसेज कर देना है, ठीक
ओके
ओके
सर।
ओके कैन यू see the slides here?
यस सर।
Okay, now please mute your mic. So let me explain this slide again. So I was just explaining that in ASD, actually we are having a single factor of safety. And the factor of safety we bring on the right hand side, and resistance of structural shape is divided by factor of safety. So as you know that we represent the load effect by a variable RA, and the material resistance is represented by Rn. And here I'm simply representing the factor of safety by F. So I have also explained that applied load effect may be of different types. Applied load means that internal force which is acting in any structural member. That may be compressive force, that may be tensile force, or that may be bending moment or shear force. And similarly, with reference to the applied load effect, the capacity would also be the different. So for bending moment, capacity will be the bending capacity. For tensile force, capacity will be tensile capacity, which is the combination of geometric resistance and material properties. So here, so what I want to say that, so whatever is the applied load effect, for example, even though the applied load is bending moment, so bending moment is the internal force which is acting in the beam. So all type of the internal resistance, they are the function of total applied load which are acting on the beam. So it means that when we analyze a beam, we analyze it for a certain load. That load may be UDL, or that load may be live load. So actually, this is a total load in your mechanics of material. You just have the information of the total load. Actually, this total load is the constituent of the dead load and live load. There might be many other type of load, maybe earthquake load, wind load, but here for the simplification, I'm just explaining with dead load and live load. It means that applied load effect is the function of dead load and live load plus any other type of load. Actually, in LRFD, what we do, we divide the factor of safety, or we convert it into two parts. One part may be F1, other part may be F2. This is just for reference, or you can give them any name. So it means that, for example, if F is 12, so we can write F as a 4 multiplied by 3. Answer will be the same. So one factor of safety is called major factor of safety, whose value is more. And F2 might be the minor factor of safety, and its value will be lesser than F1. But both F1, F2, they might have the value more than 1, because factor of safety is always more than 1. So what we do, the major part of the factor of safety, it is multiplied with the load effect, RA. And a smaller part of the factor of safety, we bring on the right hand side, and the resistance is divided by that I know, you know that 1 over f2 we can represent with a value 5. So phi value will always be less than 1. So phi value is equal to 1 over f2 or 1 divided by a minor factor of safety. So if we take the example of a simple tension member or axial loaded member, so Rn material resistance will be equal to Fy into A, just like I have explained in the ASD method. So actually this phi is referred as a strength reduction factor. So in the strength reduction factor, Rn may be Fy multiplied by some geometric properties. So we can say that geometric properties cannot be changed, because if the area is there, we cannot say that area is partially available or area is maybe available more than one. So it means that if the strength is being reduced, so we are considering that material strength is less. Okay, on the other hand, what we do, this major factor of safety, it is multiplied with the load effect, and load effect may be the combination of various type of the load. But again, I have written an index I, which is variable. It means that this factor of safety, this will not be a constant factor of safety for the dead load or for the live load. So this factor of safety will be different for the dead load, and it will be different for the live load, and also it will be different if we are having any other type of the load. So why we are using the different factor of safety for dead load and live load to make our design more realistic? Because in ASD, if we are using the constant factor of safety with dead load and live load, it means that we are also increasing the dead load maybe beyond our, some realistic point of view or engineering point of view. So here, this factor of safety which we use for the dead load and live load, they have been specified by AISC and different design methods. So actually in LRFD, what we do, we are increasing the load effect by certain factors, but at the same time, we are also reducing the material strength. So in ASD, actually, we are using the service load. Service load means that load which are not being multiplied with any factor. Just we are summing up all the applied load. But here we are increasing the load by a certain factor. So the load, when they multiplied with the factor of safety, they will be referred as factored load. But at the same time, we are also reducing the material strength. But ASD, we are just reducing the material strength by dividing the factor of safety, and we just put the limit on stress value or the strength value, which was 0.6. But unlike here, we are increasing the load, but at the same time, we are reducing the material strength. So that's why this method is referred load resistance and factored design method. So actually, the factor of safety that we use with the dead load is less. For example, this value is defined by, given by AISC is 1.2, and the factor of safety that we use for the live load is 1.6, which is more realistic. Actually, it means that the fluctuation in the dead load may not be more than 20%. But on the other hand, the fluctuation on the live load may be around 60% as specified by the code. So why we are using the smaller factor set with dead load? For example, if you are sitting in any classroom, there are 50 chairs. So if the weight of one chair is 10 kilograms, so maybe all the other 49 chairs, they will also have the variation of their weight between 9 to 11 kilograms. It is not like that if one chair is 10 kilogram and other chair will be 60, because the fluctuation in dead load may not be too much. But in live load, the fluctuation may be very large. For example, if one day a student of weight 50 kilogram is sitting, maybe by next day a student of 90 kilogram will sit. So this means that the probability of occurrence or uncertainties in live load may be more as compared with the dead load. So which are making this structure more realistic. And similarly, this phi value, which is the strength reduction factor, this is also different, and this is given by the code. For example, this phi will be called phi t sub t, means strength reduction factor for tension member or tensile loading. So this value in case of yielding, it is 0.9. But in case of the compression, this value will be 0.85. We will see when we start the design phase. And this value is again 0.75 if the failures occur due to breaking or rupture. So even though in the tension members we are considering this point as a zero point 0.9, it means that we are just reducing the strength by 90%. Unlike in ASD, we are reducing by 40% because we are considering this phi value of strength reduction factor or 1 over F as a zero point 0.6. So now this is just repetition what I have just explained. Major part of factor of safety is applied on the load and actions called overloading factor. Overloading factor means that we are increasing the load by certain factor. So minor part of factor of safety which I am referring as a F2 is taken on the right hand side of the design equation and it becomes reciprocal of factor of safety. And reciprocal of factor of safety is referred as a phi value which is called strength reduction factor or capacity reduction factor. So resistance factor phi is always less than 1 because factor of safety is more than 1. So 1 divided by a larger value will yield a lesser value, less than 1. So design equation is checked for each strength and serviceability limit state one by one. So the design equation now our will become like this. So when we are multiplying, so let me change this equation a bit. So this goes to be divided by f maybe 2 because I have explained like this way. And let's make it F1. F1 is the major factor of safety. So here RA is the service load effect or service load effect. Service load means the load which are not being multiplied with any factor of safety. When service load, dead or live, they are multiplied with factor of safety, they are called factor load and we represent the factor load with a subscript U. And Rn is the nominal moment carrying capacity mean without any strength reduction factor. So if Rn is divided by F2, so 1 over F2 is also referred as a phi or strength reduction factor. So Rn is just nominal capacity without any reduction. So if we are multiplying with phi value, so this capacity will be referred as a design capacity. Design capacity means capacity that we have considered after reduction. Same, for example, I have given you already an example. If we are having a cup to accommodate a beverage or coffee of 250 ml, but actually the capacity will be more than 250. So its capacity might be 300, but we have put the limit at 250 because we will not pour beverage more than 250. So 250 will be its design capacity and 300 is the nominal capacity. So advantages of using LRFD: behavior at collapse, including ductility warning before failure and stain hardening may be considered directly. Okay, if you are having the stress strain curve of steel, just imagine. In ASD, we just consider 60% of yield value, the maximum strength. Actually, it means that structure will fail when the stress will be equal to 60% of yield. But actually, the structure will not fail because this is the design allowable strength. Even though we are overloading the structure, the stress may be 70% of Fy. So we are still in the elastic range. But here, so for example, in tension member design, we are considering the capacity of phi value 0.9. 0.9 Fy means that if the yield strength is equal to 250, so we are considering the failure stress 225. It means that our failure limit is very close to the yield value. It means that if we are overloading it, so overloading means that there are chances that some part of the material will enter into the yield zone. So in plastic zone, we might observe some plastic deformation. So in the plastic deformation, we may have the warning before the failure. And also, if you see that strain value at 0.9 Fy will be more as compared to the strain value 0.6 Fy. So it means that this structure which we have designed with LRFD will undergo larger deflection or deformation for failure. So every type of load may be given a different factor of safety depending upon its probability of overload, number of severe occurrence, and chances in point of application. Just like I have explained that we are using factor of safety 1.2 with the dead load and 1.6 in the live load, which are making the design more realistic. It is more safe structure result due to the better awareness of structural behavior near collapse. Actually, near failure, we can estimate that what type of the failure may occur. If it is the bending, in the bending failure, so it bending moment maximum stress will occur at a point where the moment is maximum, but all the other parties will be remain within the elastic range. So we can directly predict some failure also. Results can be compared with experimental up to collapse and with structural failure in past. Actually, I told you that if you have designed a beam or any structural member by ASD, so your design load was 100 kilonewton. But when you tested that member, so it will not fail at 100, it might fail at 200 value. It means that the capacity cannot be compared with the design. And maybe actually in ASD failure will not occur actually in the field condition. But in LRFD, for example, if you have designed a member for 100 kilonewton, so when you actually test in the lab, the capacity may be 110. So it is closer. And also, if you are overloading it, so you can witness that, or you can observe that whether the failure is a shear failure or lattice failure. So what we may do, if in the field we have seen some failed structure, so we can, for example, we can investigate or evaluate the reason why this failure occurred. This failure occurred due to the maximum shear stresses or bending stresses. All the later research publications are available only in LRFD. So ASD is rarely used. But anyhow, ASD is still we are using to design some steel member. But for concrete, we have almost obsolete the ASD method. Economical in case of dead loads are larger, such as in concrete structure. So in concrete structure, LRFD become quite economical. Of course, in concrete structure, 2 by 3rd is the dead load. So since we are using smaller factor set with the dead load, so our structure is highly economical in case of the concrete. But in steel structure, the dead load are less. So maybe ASD and LRFD give the comparable results in terms of economy. So more safety than ASD if live loads are greater. So if live loads are larger because we are using high factor of safety with the live load, so the result will be more on the safer side. Plastic design may be incorporated with few changes. What does the plastic design mean? Plastic design means that if I'm considering the material strength equal to or more than yield strength or more than its elastic limit, then this design will become plastic design. The convenient elastic analysis for load is generally used in this method. Okay, it's mean if I'm using the material strength equal to 0.9 Fy, so I'm still in the elastic range. So all the theory of elasticity and elastic formula, for example, shear formula and bending formula, deflection formula are applicable for the analysis and design of structure. The design procedure is similar to ASD with only slight modification that I have explained. Using LRFD steel and concrete design become consistent with each other. So I told you that in steel design and concrete design, so we can achieve the same economy level. What are the disadvantages? Elastic behavior considered for load analysis and ultimate elastic behavior for material strength are not compatible. However, percentage difference is very less. Actually, if I say that we are using zero point 0.9 Fy, the strength, so zero point 0.9 Fy is very close to the yielding part or yield. So it's mean that within that zone, so our material might behave a little bit plastic in nature. So there might be some permanent deformation, but the difference will be very less. So most of the experienced engineers, they are available, they are having experience in AST because LRFD is relatively a new method. Maybe it is, maybe people they have switched to the LRFD maybe 10 years back. But if you are having any experience and old engineers, so they are all having the experience in AST. All old book design aids, maybe all 15 to 20 years old books, you will only see the ASD method, no LRD is available. Validity of previous design is still to be checked according to ASD. So actually, if one building is designed 30 years ago or maybe years ago, uh, so in that time maybe that building was designed by considering only ASD method. So it means that if you want to evaluate it perfectly or accurately, so we have to use the ASD method. Otherwise, uh, we cannot properly estimate it. So plastic design, I'm not going to explain, but I will just give you the one clarification. You can read it and understand yourself. Plastic design is similar to what I must say LRFD design. We can increase the load by a certain factor of safety, but actually the material strength we are not using less than equal to Fy. So phi Fy, this value will be equal to either yield or more than yield value. So that method will be called plastic design. If I consider material strength more than or equal to yield value, then LRFD method will be referred as plastic design. So same as LRFD with difference that plastic analysis is used for the load analysis. So plastic analysis you will study in maybe in structure analysis. So this is the best available method. Actually here we are considering the actual failure behavior in design and analysis, so we can compare both methods. So incompatibility, load analysis and material behavior is removed because we actually know what type of the failure occurs. So based upon the failure, we actually design that method. This is very lengthy, even for computer application due to plastic analysis. So plastic analysis is simple for maybe analysis of single beam and column. But if we are analyzing a complete building, then this method is very lengthy, so we cannot do without any computer software. So what is current situation? Portion 3 design engineer have almost shifted to the trend design for LRFD. ACI has discontinued AFD as an alternate method for design. For steel design, still we are using the both method. Some parts we are still designed by using ASD. For example, in our design classes, you will see that I will explain some of the members we are designing by ASD. So when the method will develop for LRFD, maybe we have to discard ASD method for design of that member. Is AISC, American Institute of Steel Construction, has only issued combined LRFD ASD specification in 2005 after AISC ASD 1988. So the last time in 2005, so AISC has published two specifications side by side. They have given the example for the specification for a particular member design by adopting the ASD method and LRFD. Most recent LRF, AISC, LRF specification were issued. Actually, now this specification they has been revised in 2018. So this line you can discard. This specification has been revised in 2018. AISC has included ASD only as alternate method in specification. So in 2005 specification, so basic design method was LRFD. So ASD, it was just a second option or an alternative method. So ASTO has shifted the bridge and other design to LRFD completely. The latest H2 ASD specification will only be used for evaluating the previous design. So for the evaluation purpose, we can use ASD, but for the new design, we have to use LRFD. Most American states have opted not to use ASD for bridge design after 2005. And British specification for concrete design are also according to method. However, they refer it as a limit state design. Actually, in British code and European code, LRFD, load resistance factor design, it is referred as limit state. We have put the limit on strength and also on the load. American universities are only teaching LRFD now. Universities of Pakistan are also teaching this method for concrete design. So for the concrete design, people they have almost new engineers shifted to LRFD. But for steel design, some University of Pakistan has switched to this method. So it is expected that in the future only one method will be used for practical design, which is LRFD. And for research work and high importance structure class design is the most best method. So this was the scenario. So here I would like to have maybe some question. If you are having some question, then I will switch to the next phase of the lecture. So if you are having question, you can use the raising hand option. Anybody is having the question? Yes, Uzair Shafi, please ask.
सर आप कह रहे थे कि LRFD में हमारे पास डिफ्लेक्शन वगैरह जो है वो ज़्यादा होती हैं या विजिबल वगैरह हो सकती हैं, तो सर LRFD में हमने अगर चाहे जो हमारी स्ट्रेंथ है वो तो कम ही रिड्यूस किया, लेकिन दूसरी साइड पे हमने लोड जो डिज़ाइन के लिए अप्रूव किया उनमें भी तो फैक्टर ऑफ सेफ्टी ज़्यादा दे दिया, तो वो फिर एक तरह से बैलेंस नहीं हो जाएगा कि उस ASD की तरह का ही सिस्टम बन जाएगा?
नहीं नहीं नहीं, उस तरह का नहीं सिस्टम बनेगा. Okay, I understand. Actually, let me clear. I'm in ASD. I'm not in, unlike ASD, I'm not increasing the dead load and live load by the same factor. Just I have to make you understand by using some equation. Okay, let's suppose, let me make the duplicate of this slide. Okay, here let's suppose dead load is and live load is 100. And this factor of safety is 1.667 actually this is. So if I am multiplying if I am multiplying with 1.6, so what will be the answer? 300 when it is multiplied, that will be 320. plus 160, isn't that? And that should be less than equal to 5 Rn. So the total answer will be equal to, what is the total answer? 480 maybe. So total load is acting 480. So this is the equation in our AST method. Maybe you will agree with me. If I have considered the same load, but here, if I'm using this LRFD method, in this case, so it's period I have to use 1.2. Maybe multiply by 300 plus 1.6 multiply by 100. So total load will be, sorry, मैंने कुछ mistake की यहाँ पे. Yes. So this will be 240 plus 160. What is the total load here? The total load here, it will be less. So that will be maybe 300 only, 400. So it means that if I just compare the load, so I am, because I'm using the other side of the equation as a constant. So it means that as compared with the ASD, I'm using a smaller load value in the design for the same material strength. It means that if I'm overloading, there are chances that the material, uh, what I must say, I'm approaching to the yield value first in ASD. But if I'm overloading, if I will increase this load by 80, this load may be 480. If I'm increasing this load by 80, this load will be 560. It means that ASD is always over design. Over design means that conservative. I'm using the higher load value. It means that that cannot be compared because I'm using different factor of safety with different load. But let me find that if I'm having any stress strain curve. So I will explain you from the stress strain curve of steel. Maybe I might have in this today's lecture. Not here. So just understand, if we are having this stress strain curve, on stress strain curve, if you are having 0.6 Fy, from add value 0.6 Fy, if you are coming down, if you drop a straight line, so corresponding to 0.6 Fy, strain value will be less. I'm just explaining that close to the failure. Failure doesn't mean actual failure, specified failure. Specified failure means that in ASD I have put the failure limit 0.6 Fy and in LRFD 0.9 Fy. So strain value at failure limit in LRFD will be more as compared with the ASD. If I'm approaching to the failure, this means that LRFD will undergo larger deformation and it will be, behavior will be more ductile as compared with the ASD. So you understand?
यस सर, लेकिन सर इसमें LRFD में हम वो जिस तरह आप बता रहे थे कि फ्रैक्चर वगैरह के लिए 0.75 और
वो
यील्डिंग
भी
के लिए
देखेंगे,
0.9 वगैरह.
वो देखेंगे, वो भी नहीं, वो भी नेक्स्ट जब आएगा वो बताऊंगा. Fracture
ओके.
actually, वो इसमें mean that rupture is the most critical case. You understand? But in ASD, in fracture, the limit is 0.6 again. In ASD, if the limit is 0.6, but in fracture, LRFD is 0.75. Again, I'm considering the larger limit. So this thing, actually, they will be clearer when we are gradually entering to more toward our advanced topics. Next, कोई है किसी का question? Anybody else is having the question? अगर किसी का लाइक नहीं है तो then I would like to maybe conclude. So today सबसे पहले मैं so in today's design class, first of all, I will cover up maybe topic of theory class that I have missed today for 30 minutes. Then I will start the design phase, inshallah. So till then, uh, maybe you might have some break. So inshallah, I will see you at 1 p.m. So, okay, Allah Hafiz.